Good. All right. So we were, let's see. Stop. Come on. 16. Okay, we got to where we were calculating a test statistic. Let's should we do like a quick review here? What we had done? Let's just do a quick review as to what we had done. Okay. So we were doing kissing couples, and we described, let's do it in single page here. Okay. We described what it was that we're trying to do in words. So we were trying to find out what proportion of the adult population turns their head to the right when kissing. And we identified that as pi, that is our population proportion. Then we learned about the null hypothesis, okay, which is what we are trying to nullify. So in this particular example here, the researchers, they wanted to see, well, is it 50-50? Everybody, half the people turn their heads to the right, half the people turn their heads to the left. So they made a statement, a hypothetical statement. They made a hypothesis, the null hypothesis, H sub 0, that said pi is equal to 0.5. Half the people left, half the people right. So that was our null hypothesis. And then we have three choices for an alternative hypothesis. One is that pi is going to be less than 0.5. One is that it's going to be greater than 0.5. And then the other is that it's going to be not equal to. So our alternative hypothesis is always just that it's either less than, greater than, or not equal to. Okay, and again, I just want to point out, nowhere are we trying to prove or test whether or not the parameter is equal to 0.5. We can't know that for sure. But what we're trying to do is trying to see whether we can reject the hypothesis that it is equal to 0.5, whether we can reject that. So we got so in this particular case, our alternative hypothesis, the researchers were looking for whether it is greater than 0.5. So we tested our conditions. We tested to make sure that our n times pi was greater than 10, and our n times 1 minus pi is greater than 10. And those were okay, so we could use the central limit theorem. And we also tested that the study was involved randomness. So that was okay. So as long as it's random and the sample size is big enough, we can use the central limit theorem. Am I going too fast? I'm just kind of reminding you. We're okay? Yeah, this is all in the video I sent out yesterday too. So, so we made ourselves a diagram. And what's different here from the diagrams we were making with confidence intervals is that with this diagram, our center is our null hypothesis, is what we are hypothesizing the population parameter is. When we were doing the confidence intervals, let me just make a little picture over here. When we were doing the confidence intervals, we had a diagram. Isn't that that is a beautiful normal curve right there. I don't usually make them that nice, but that's really a nice normal curve. When we were doing confidence intervals, the center was our p hat. And then the standard deviation was really the standard error based on p hat. And that's how we made our lines. That's when we're doing confidence intervals. When we're doing a test of significance, the center is our hypothetical pi. It's our null hypothesis. And the standard deviation, we use pi to calculate it, not p hat. So you got to make sure you're clear on that. When you're doing a test of significance, we're using pi to calculate these things. When we're doing a confidence interval, we're using p hat to calculate these things. So we made our diagram. Yeah, everybody okay with that question? No, we're good? We're good? Okay. All right. So we made our diagram, and then we said, okay, well, now I did have a test statistic. I mean, I did have a sample, and that sample of 124 people, 124 kissing couples. So actually, if it's 124 kissing couples, that would be 248 people, right? Because you have to have two to kiss. Their proportion, their p hat, was 0.645. So I put 0.645 on my diagram, and I found out, well, it's way the heck over here. It's way over here. I can see that it is more than 1, 2, 3 standard deviations away. So I want to find out exactly how many standard deviations away it is. I calculate the z-score. So 0.645 is the value that I got. So this is x minus x bar, which is my pi, my null hypothesis. And I'm dividing it by my standard deviation. And I find out that that is 3.22 z-scores away from the mean. This z-score is called my test statistic. Honestly, I think that's poor terminology. Because when I'm thinking about what's my test statistic, I'm thinking, well, that would be my p hat. That's my statistic, right? But in a test of significance, the test statistic is the z-score of the p hat. Z-score of the p hat. That is my test statistic. So I just kind of like zoomed through all that. I'm going to stop and just see if there are any questions up to here. Are there any questions about where we got to last time? And you guys know how to do all this. It's just a matter of getting the terminology correct. Okay, seeing none, let's proceed. Okay, so we calculated the test statistic. And the next step that we need to do, oops, wrong one. What? How did that happen? I don't want that. Here's our test statistic. The next step is, the next step is we're going to calculate the p-value. Okay, so have you ever heard that term, p-value? Anybody heard that other than in statistics class? Anybody ever heard that term? No? Okay, you will find this in newspaper articles about surveys. You're going to find this if you're taking psychology, any sign of social sciences. They're going to talk about the p-value. All right, so first of all, let's see what they did here. They said, okay, we know the z-score. I'm not going to bother with that. So let's go down one more here. So I have to calculate the p-value. P-value stands for, at least in my understanding, probability value. What is the probability? Assuming that the null hypothesis is true, of getting a test statistic at least as extreme as the one we actually observed. And extreme means in the direction of the alternative hypothesis. So, you know what? I like my diagram better. I'm going to use my diagram. So here's, I don't know, my diagram's looking a little bit crowded now. I think I'm going to change my mind. I'll use their diagram. We know that our test statistic is way out here at 0.645. We know that the center here is pi, and that is equal to 0.50. This is our null hypothesis. And we know that the z-score for this is equal to 3.23. So my alternative hypothesis is way far to the right of my mean. It's far greater than my mean. So I want to find out, what is the probability of getting 0.645? What is the probability of getting a z-score of 0.323 or greater if in fact my null hypothesis is true? If pi equals 0.50, what's the probability that I would get 124 couples and they would have 0.645 turning their heads to the right? Well, what tool am I going to use? Magic bulb. What tool am I going to use to calculate the probability here? Let's see if we can get an answer. Crystal, can you tell me what tool I'm going to use?
Sorry, can you repeat?
Yes. So I have a z-score of 0.323. My alternative hypothesis, my H sub A, is that pi is actually greater than 0.50. And my p hat, the statistic that I got, was 0.645. And that has a z-score of 0.323. I want to know, given this diagram, with the center being my null hypothesis of 0.50, what's the probability that I would have gotten 0.645 from my sample? That's a lot of words there, Crystal. Can you follow me? Can you answer it? Or was that
actually, I couldn't see your screen.
You can't see my screen?
Yeah.
Oh, well, then that would make it difficult. So hang on and listen, and we'll see how it goes.
Okay.
Okay, so Kathy, what tool am I going to use to calculate the probability that I would get 0.645 or greater if the actual population parameter was my null hypothesis of 0.50?
You would use normal CDF.
That's exactly right. Because normal CDF, my input is a z-score on the left and a z-score on the right, and that gives me a percentage. That gives me a probability. So I think we can do that. Normal CDF, that's number 2. My left z-score, because it's right here and I'm going to the right, my left z-score is 3.23. And my right z-score, since I'm going as far as I can possibly go, greater than 3.23, is going to be 99. Wow, that's a really low number. I don't even know how small that probability is. Wow. That would be, that would be 0.0000619. So if I was turning that into a percentage, that would be 0.0619%. That is my p-value. My p-value is equal to this probability right here. Or if we wanted to do it in scientific notation, we could go 6.19 times 10 to the negative 4th. Look familiar? Same thing we've been doing? Yes, we just have a problem now we're calling it a p-value. So I'm going to summarize my conclusion here. Well, actually, let me ask a question. If my p-value is 0.000619 or 0.0619%, do you think I'm going to be able to reject my null hypothesis? My null hypothesis is that the population proportion for kissing couples is 50-50. I did some data gathering and I found out that actually I got 0.645 from my sample of 124 kissing couples. Based on that, would you reject the null hypothesis or would you not reject the null hypothesis? What do you think? Let's take a test. Let's take a vote. Who votes to reject? The null hypothesis is that the population parameter is 0.50. Who votes to reject the null hypothesis? Really? Everybody votes to reject the null hypothesis? Kaylee, you're kind of iffy on this.
Yeah, I'm kind of confused. I wasn't here last week, not last week, last class. I haven't watched the video yet, but I'm getting there.
Oh, okay, that's fine. All right. Well, everybody wants to reject the null hypothesis, and I want to reject the null hypothesis. I'm saying, don't tell me that people kiss 50-50 left to right. That you know, I did a pretty good sample. I got 0.645 from my sample. It's like way off the charts. So no, I think this null hypothesis is wrong. Right? So I am voting to reject the null hypothesis. So how do we do that? If the p-value is small, which this is a very small p-value, it was 0.000619. If it's small, we reject the null hypothesis. If it is not small, then we fail to reject the null hypothesis. Those are our two choices. We're either going to reject the null hypothesis or we're not going to reject the null hypothesis. So how do we know what is small or not? I mean, you know, some people think 10 is small. Some people think 5 is small. I mean, you know, how do we know? Well, that will generally be defined in the beginning of the study. A p-value above 0.1, you're not going to reject it. But a p-value smaller than 0.05, that is reasonably strong evidence against the null hypothesis, and a p-value below 0.01 is very strong evidence against the null hypothesis. So let's think about that for just a second. Let me just see. Yeah, okay. So what I'm saying is that if I have my diagram, and here is my center, and my center is my null hypothesis equals, my null hypothesis is colon, pi, is my null hypothesis is pi equals something. And I find out that I'm way over here. if I have a p-value, if this area under here is 0.05 or less, I reject the null hypothesis. I think that's kind of what we need to remember right now. When we're looking at a study, let's make sure I got this here. They will give us what is called an alpha. And this is telling me what is the p-value that will allow us to reject the null hypothesis. I really am sorry that there's so many like double negatives in this section, but that's just the way they are in statistics. So if I had an alpha of 0.10, then I'm saying that a p-value that is less than 0.10 allows me to reject the null hypothesis. If I have an alpha of 0.05, it means I have to have a p-value that's smaller than that. I have to have a 0.05. So a 0.10 might be over here, giving me this much right here. This would be a 0.10 probability. A 0.05 would be over here. So it would be a smaller probability. And then a 0.1 would be an even tinier probability in order to reject the null hypothesis. And you'll notice that if I have an alpha of 0.10, so I'm saying right here, this is 0.10, well, this is 10%, and this is 90%. So it's similar to a confidence interval, but not exactly the same thing. Let's see if we can't do a problem. So kissing study, yes, we rejected the null hypothesis. Does this study provide convincing evidence that kissing couples turn to the right the majority of the time? I think so. I mean, it's a pretty big sample size. Okay, this is kind of like, again, one of these double negative sentences that we're going to use. The p-value is not the probability that the null hypothesis is true. That's where people get confused. The p-value is the probability of obtaining the sample that we got if the null hypothesis is true. So the p-value is referencing the likelihood of getting this if the null hypothesis is true. So the p-value is very small for getting that if this null hypothesis were true. Is this like being like very confusing? Or is this making sense? Or do we just really need to do a couple more problems and then get it straight through our heads? Thank you, Emily, for answering me. All right, let's do that. Okay, so we're going to continue on kissing couples, and we're going to use the magic bowl. Okay, and again, we're covering all of our objectives, which is how do we do a test of significance. So let's kind of call our test of significance down to here. And start with this problem. Okay, so let's try that. Okay, so we're going to reconsider the study. So they noted that other right-handed tendencies appear in approximately 2/3 of the population. So what they're saying is, you know, they're not making a judgment right now about kissing couples, but they're making a judgment. They say, well, there's about 2/3 of the people are right-handed and 1/3 of the people are left-handed. So so I don't know whether it's going to be greater or lesser than 2/3. So if I think that it might be 2/3, my population proportion, how would I write the null hypothesis? Remember, over here, null hypothesis is always that I have a parameter, in this case pi, is equal to a hypothesized value. So I've kind of noted that 2/3 of the population like throw right-handed. Maybe that applies to kissing. How would I write the null hypothesis in this situation? So Mila, how would I do this?
So you would do the HO, and then it would be pi equals 0.66 repeated.
Very good. So I would write my null hypothesis is that pi is equal to, I'm going to use 0.67. Come on, go away. Okay, but they wrote 2/3. I'm writing 0.67. Right. That is my null hypothesis now. Is everybody okay with that? Was there a question? No, we're good with that. Okay. Well, I want the alternative hypothesis to represent that the population proportion is not 2/3. Okay. So looking at my three options here. Uh-oh, there's a mistake on my options. Not equal to. That should say not equal to. How do I write my alternative hypothesis? I want to write my alternative hypothesis in proper language here. So Emily, how do I write it?
Could we say H subscript A is pi is greater than 0.67?
Read the question. Read part B right here.
Is not equal to 0.67.
It's not equal to 0.67. Are you with me there? Right? This is going to make a big difference. Greater than and less than are going to have one way of doing it. Not equal to is going to have a slightly different way of doing it. Okay? Is everybody okay with that? So I now have my null hypothesis and I have my alternative hypothesis. So let's take this and go to the next step. Okay, good. Well, now I have a new hypothesized value for pi. Are my technical conditions still met? Did I meet my technical conditions? How am I going to calculate whether I met my technical conditions here? Angelica is not here. Mila, again, you are here. How am I going to test my technical conditions?
You would use the formulas n times pi is greater than equal to 10, n times 1 minus pi is greater than equal to 10. And
That's
we
exact-
also have to know whether it was selected randomly.
That's correct. Well, we know they were collected randomly, so that was good because that was in the beginning of the problem. But is n times pi greater than 10? Well, my n is 124, and my pi now is 0.67. Yeah, 2/3 of 124 is definitely greater than 10. And 124 times, well, 1 minus 0.67 would be 0.33. So 1/3 of 124 is also greater than 10. So I think my technical conditions are met. I think we're okay with that. Yep. Okay. So now I need to compute a test statistic for the hypothesized value. Okay. So remembering that my p hat was equal to 0.645, I'm going to make my picture. So we met the technical conditions. It's going to be unimodal and symmetric. And then what value is going to go right in the center here? Emily. What is this, like the Emily Mila day here? Okay, what value is going to go in the center there?
Would it be 0.67?
It would be 0.67. Very good. Pi goes in the center here when we're doing our test of significance. So I got 1, 2, 3, and I got -1, -2, -3. So this is pi. This is 1, 2, 3 standard deviations, -1, -2, -3 standard. Well, I need to figure out how am I going to calculate my standard deviation. So Sandra, can you help me? How am I going to calculate my standard deviation?
You're going to use the z-score.
I don't know the z-score yet. I have to calculate my standard deviations before I can find my z-score. So look at your formula sheet there.
Would it be p hat
Keep going.
e over n?
You're getting kind of close, but not quite.
Hold on.
Okay,
Check my notes.
go. That's a good idea.
Oh, okay. Is it? I think I have it. Is it pi?
Go ahead.
Parentheses 1 minus pi parentheses over n, and on the top it's all squared, or not squared, but the square root.
Square root of all that. Yeah. So I have a different pi than I did before, because before I was using 0.5 as my pi. Now I'm using 0.67 as my pi. So I'm going to go 0.67 times 1 minus 0.67. I'm going to divide that by n, which is 124 samples. I'm going to take the square root. And I find out my standard deviation is, let's call this 0.042. Before it was 0.045. So let's go 0.67 plus 0.042 plus 0.042 plus 0.042. So I have 0.712, 0.754, and 0.796. And then going the other way, I have 0.67 minus 0.042 minus 0.042 minus 0.042, and I have 0.628, 0.586, and 0.544. Okay. When I'm trying to find a test, let's compute our test statistic now. Let's compute our test statistic. Let's do this too. Let's put in, let's sort of the magic bowl here. So Kathy again, Kathy, 0.645, where is that going to go in this diagram?
Between the -1 standard deviation and pi.
Yep, I think it's going to fit in here someplace. So 0.645 is going to go right there. And I need to calculate my test statistic. So Kaylee, are you good on this, or should I just kind of go to somebody else because you missed the other lesson?
I think I'm following along.
Okay, great. So how am I going to calculate my test statistic here?
Don't we have to run the z-score?
The test statistic is the z-score. This is good. Okay, go ahead. So how am I going to do it?
You have to do z is equal to 0.645 minus 0.67 over the standard deviation, which is 0.042.
Very good. So my test statistic is, I'm going to go 0.645 minus 0.67. I'm going to divide that by 0.042. And then I'm going to, oh, that's it. I was going to take the square root. I don't want to do that. So my test statistic is, let's call it negative 0.595. Negative 0.595. Okay, so let's write. So is everybody okay with that? And that makes sense. It's between 0 and -1. Are we okay with that? Okay, now here's where it gets a little bit different for when I'm finding, when my alternative hypothesis is that pi is not equal to my my h sub 0, my 0.67, is I need to find out what's the probability that it is, let me say this properly. I want to say it properly rather than mess you up. Okay. If I'm saying it's not equal to 0.67, then I need to look at it on both sides. My p-value, that is the probability that I would get something like this randomly, is actually the shaded area on both sides of the mean, not just the one greater than, not just the one less than. I have to look at both sides for my alternative, because I'm saying not that it's greater than or not that it's less than. I'm saying that it is not equal to. So I have to cover both sides when I say not equal to. Well, I know that if I'm saying it's not equal to, and my test statistic is negative 0.595 standard deviations this way, I have to look at it two-sided and also go positive 5.95 standard deviations that way. So I'm trying to find out what is the probability that I would get 0.645 or less, or whatever this number is here, or greater, randomly, if my alternative hypothesis, if my null hypothesis was 0.67. So I have to go both ways on this. Well, how am I going to do that? Well, I'm going to do, I got my z-score right here. So I can go, let's do this side first. I can go normal CDF, negative 0.595, comma, negative 99, because I'm going in this direction here. And I find out that the probability of it being that far away on the negative side is, so this over here is 0.276, so about 27.6%. Let's call somebody else in. Even we have very minimal choices, but let's find it. Susie, what's going to be the probability over on this side?
Wouldn't it be the same because it's unimodal and symmetric?
Very good, very good. It's going to be the same. So I just need to multiply this by 2. So I'm going to go times 2, and I get my p-value is 0.5518. P-values are always positive. P-values are always positive. So if this is my p-value, I have a 55.18% chance of getting a number like I got randomly. Are we going to reject the null hypothesis, or are we not going to reject the null hypothesis? So how many people vote to reject? And how many say not reject? So my null hypothesis was 0.67. I got a p-value of 0.5518. How many people vote to reject the null hypothesis? Nobody wants to reject the null hypothesis? How many people say not rejecting the null hypothesis? Everybody says not rejecting the null hypothesis, and you're absolutely right. This is too high of a p-value. I could have absolutely gotten that value with the null hypothesis of 0.67. So I cannot reject the null hypothesis in that case. Okay, we did. Well, these two, right? We did that. Oh, she got 0.301. Why did she get 0.301? What did she do different from me? She just must have used a slightly different, she just probably didn't round. So I'm okay with what we got. Okay, so when we're doing not equal to, we find the area on both sides and we add them together. We multiply it by 2. Okay, so do we fail to reject? Yes, we don't reject the null hypothesis. I don't know what even she's saying here. What is she saying here?
Mr. Jenkins?
Yes, please.
I have a question. When you put it into the normal CDF, why didn't you put -99 first and then negative 0.595?
You know why I did that, Susie? It's because I was doing too many things at once. So I should have done it that way. My bad. I should have, and if we did that, well, what will we get? Let's just see here. I should, that's the left Z and the right Z. I made a mistake. I hope I didn't mess anybody up. If we, well, I'll tell you what we can do here. So it should have been -99, comma, -99, comma, -0.595. And that should probably give us a positive number. Yeah, that gave us a positive number. So that's a better answer. Huh, I think we just lost somebody. Okay, whatever. But when you multiply it by 2 and you make it positive, it turns out the same. But you were right. Okay. So the probability of obtaining a sample proportion at least as extreme as 0.645, assuming that pi is actually 2/3, it's not small. I could definitely have done that. So it could have occurred randomly. So I cannot reject the null hypothesis. So how are we doing? We're doing time-wise. Let me see here. We're done at 12:10. Okay, so here's what we're going to do. We're going to stop because I don't think there's enough time to do this problem adequately. And that'll be a good place for us to start again when we get back from Easter break. All right, so as I've been telling all of my classes, really, you just have such wonderful things to think about over Easter break. You can think about null hypothesis, you can think about alternative hypothesis. How does it mean? How do I reject it? How do I accept? Or don't you never accept it? How do I object? How do I accept it? How do I not? How do I reject it? How do I not reject it? All these great things that you get to do over Easter break. So extra time for lunch. Have a good Easter break. And I'll see you when we get back. Yeah. Okay. Later.
Thank you.
Thank you.
You're welcome.
All right, everyone, can you clean the desks before you go? Thank you.
Okay, so Mr. Oriana, are you there?
Yes.
Okay, so here's what we need to do about the TI emulator.
You're recording, by the way.
I'm sorry. What?
You're still recording.
Oh, I am. Let's stop recording.